In this presentation, we consider how you can compare DC values to AC values. So before we do that though, I wanted to point out that it's possible to combine a DC voltage along with an AC voltage in a circuit, and in this case they're connected in series and they're connected to a resistor. So Ohm's law is still satisfied, and so the voltage across this resistor would just be the, the current times the resistance, and the voltage is equivalent to the combination of these two voltage supplies, because Kirchhoff's voltage law is also satisfied. So I have a 10 volts of DC, and I have an oscillating source that has 15 volts, and it's a sine function, and the phase shift for that sine is just 0, so it starts off at time t equal to 0 to 0. And the question is for us to look at this, this waveform and see if we can draw a picture of it, and also to understand what's going on. So when you have something that is DC in combination with AC, we can imagine that that AC waveform is simply shifted by the amount of the DC when we draw our picture. So here's my sine function, and normally it would start off at time t equal to 0 at 0, but it has been shifted 10 volts at time t equal to 0, and then the whole waveform is just shifted. So if we wanted to know what is the maximum value, what is the peak value, right, the minimum value, and the average value, we could think about certainly the peak value and the minimum value. So sine function is a maximum at 90 degrees, or it's equal to 1 at that value. So the maximum that this sine function can be, or this voltage can be, is 15 volts. And so if I add to it 10 volts, the maximum is going to be 25. So essentially I have a sine function that is oscillating about that 10 volt position, and the maximum value up here is going to occur when the sine function is a max, and it's going to be 25. In the same regard, I can find the minimum value, because the minimum value would occur when sine is a minimum, and sine as a minimum value is -1. So if I put in a -1, I would have a -15 plus a 10, and that would give me a -5, which is right here. Now the more important question is, what is the average value? And so it turns out, over one cycle. So the average of a sine function over one cycle, just alone by itself, is always going to be 0. Because when you look at a sine function, it always has the same amount of positive values as it has negative values, if we were just looking at it about the 0 axis. And so essentially, if we're looking at the average, this sine value goes to 0, and the average is just the DC value. So how are we going to compare AC and DC if we have a combination of both of them together, and the average is going to be whatever the DC value is? In other words, the average voltage is not going to contribute, the sine part is not going to contribute. So it turns out that when we are measuring average values, what we're actually measuring is a DC value, an average DC value, using a voltmeter. That means that we could take the voltmeter, we could have it set for DC, we connect it across a device, and what it's doing is it's measuring the average over a very small time interval. So suppose that we had a waveform that was a function of time, and even though it's a really small time interval, it is changing with respect to time, and we want to know what is the average. So we have to go back to what we learned in our math courses, and we have to realize that if we have something that's a function of time, if we want to know the average, we have to take the area under the curve and then divide by the base. And so in this case, I have current, which is a function of time, and it is changing with respect to time in the sense that sometimes the current is positive 2 amps. So over 3 milliseconds, it's positive 2 amps. And then it drops immediately to negative 1.5 amps over a period of 4 milliseconds until it reaches 7 milliseconds. So this is relatively easy to calculate the area under the curve if I want to know the average. So I have a rectangle, and so I could do, base times height. So my height is 2 amps and my base is 3 milliseconds. And then I would add to it for this cycle the other rectangle, which is below the axis. That's going to be a negative area because the height here is negative 1.5 and the time interval is 4 milliseconds. And then I would divide by the time interval, which is a total of one cycle is 7 milliseconds. So it turns out gives me 6 minus 6 for the area, or a total area of 0, which means that my average is 0. So if I were to use a DC meter to measure the current in this case, in the DC value, it's going to read 0, even though sometimes I do have current that's positive and sometimes I have values that are negative. And so I need to be able to think about this and how then can I compare DC and AC. It's even more obvious if we look at something that's sinusoidal. So it turns out that if you have a sinusoidal varying function and you look at the average over one cycle, sine and cosine are always going to be equal to 0 if you average them over one cycle. And this can be found by using some integral calculus. So if we go back to what we just said about the average of a function, we have to calculate the area under the curve over one cycle. And in calculus, the area under the curve is the integral of the function. So here I have something that I cannot just say that the area is base times height. I have to use calculus. Now we're not going to actually have to use calculus here to do this, but to show you this example, it's important to go through the steps. So the average of a function in general, we often write f with a bar on it, is just the integral of that function over one period divided by the length of the base, which is just integrating over that particular interval, which is going to give us the period on the bottom. And then I would have to integrate that function with respect to time over one period. So if you could imagine that our function is a sine function, we have the same amount of positive values in my sine function as we have negative values, and so they are going to cancel out. But I could explicitly write this down as the integral of sine omega t. The omega is just 2 pi over the period, and I have to integrate that over one cycle. Now I don't have this written down, but the integral of sine is a negative cosine, and when you put in the values for the period of 0 and a value of 0 and a value of the period, you're going to get a value of a cosine of 2 pi minus cosine of 0, which is just going to give you a 0. But it's really just obvious from looking at this picture because of the symmetry that the average, or the area under the curve, is going to be 0 for a sine function. So using average values to try to compare AC and DC is not a very good way of doing it, because for AC, the average value is always going to be 0. So we have a better way of comparing AC and DC, and the way that we do that is by comparing the power output over one cycle for DC, and how is that equivalent to the power output over one cycle for AC. So if we imagine going back to a voltage supply that is a constant voltage supply connected to a resistor, it has a certain amount of power that comes out. Now according to Ohm's law, V equals IR, and so there's going to be some current in this circuit, and the power in that circuit is just the current squared times the resistance. So this is something we want to keep in mind, that in general for DC values the power is current squared times resistance, and it's a very constant value. So over one cycle it would measure the same value no matter what, because it's just a constant value. So now we'd like to compare that value for DC to what AC would look like. So I have now an alternating voltage supply, and it's connected to a resistor. It would produce alternating current. Ohm's law is still valid, so when the voltage is a maximum, the current is a maximum, because I just have this resistor in the circuit. And so if I make a plot of what the current is doing with respect to time, it's a sinusoidal varying function. So over here is my sine function, right? and that is 1 cycle of my sine function, my current. But the power is equal to the current value squared times the resistance. The power is still a function of time, but it is the current squared. And when you square that current, sometimes the current was a negative value, but when you square it, it becomes positive. So over 1 cycle, the power oscillates, and it's always a positive value, and it reaches some maximum value. And the maximum power would just be the maximum current squared times the resistance. And over 1 cycle, which is actually sort of 2 bumps, I guess you could think about it that way, of the power function, the average is just equal to half of the maximum. And we're going to see where this comes from. And so what we want to do is, how do we compare this average value to what the power was for DC? But let's see how we get that average power first. So we would want to write down what the power is as a function of time. And so if I plug in my current as a function of time is a maximum value times sine omega t, and I square those values, this is my current squared, and then times the resistance. And I know that I need to figure out what is, if I want the average power, what is the area under this curve for power? So I need to know the area under both of these curves, and then I need to divide by that time interval. So I'm going to have to, because this is a function, I'm going to have to integrate sine squared. And it turns out, if you remember back to calculus, that to integrate sine squared, you need to use a trig identity. And so sine squared can be written as 1/2 1 minus cosine of twice the angle. And that's just a very standard trig identity. So I can write that, pull the 2 out front, and it's the maximum current squared, the resistance over 2, and then 1 minus cosine 2, 2 times the angle. So now I have something that I want to integrate this function over 1 cycle to calculate this average, and then I can figure out what the average power is. So my average power is just the integral of this function, which is my power function right here I've plugged in, over 1 period. So I can integrate this, and when I integrate this, the first, everything out front is a constant, and then I have this term on the bottom of the period, which is a constant, so I put all the constants out front. And then when I integrate 1 with respect to time, I get the time. And when I integrate negative cosine, I get a positive sine value, and then I have to divide by the constant that's in front of the time. So here is the integral of 1 minus cosine omega t. Now I need to put the limits in over 1 period, and so when I put the upper limit in for the period here, for the time, I get a period. When I put the period into the sine function and I plug in that the angular frequency is 2 pi over the periods cancel out here, and I end up getting sine of 4 pi. Well, sine of 4 pi is 0, so this term in red is just 0. When I put the lower limits in, I put a 0 in for the time, I get a 0. When I put a 0 in here for the sine of 0 is also 0. So everything in red is just 0. And I end up getting that the average power is just this term out front. The periods here cancel, so it's just the maximum current squared times the resistance over 2. So we go back up here, this is what we found the average power is, and it's basically half of the maximum power. So why do I have this other piece here? So remember that when we looked at DC, the DC power over 1 cycle, and it doesn't matter because it's a constant value, is just the current squared times the resistance. So I want to be able to write the average power for AC as being something that's equivalent to DC, where DC equivalent is just current squared times resistance. So this current is some effective current that is essentially equivalent to a DC value. So here's my power with my effective values, If I compare these two expressions, I can cancel out the resistance, and I get that the effective current, this piece right here, that's the effective value for DC squared, is equal to the maximum value of the current that's varying sinusoidally over 2. And then according to Ohm's law, I can have the same expressions for the voltages. So the effective value for the current is just the maximum current over the square root of 2, and then effective value for voltage is the maximum over the square root of 2, and so on. So what does this mean? The maximum value is the maximum value in your sine function. How big does that sine function actually get? That's your maximum. The effective value is what is this AC over one cycle equivalent to in DC. So the effective value is this is what the current would be effectively equal to in DC if you had this maximum current here. I can essentially then also switch it up. So if I knew the effective value, I can solve for the maximum value. This is just rewriting the equations and solving for different variables. So just to give you an idea of how this works, we often say that when we plug something into an outlet, that we're plugging into AC for sure. We know that, and we have 120 volts. And that's actually an incorrect statement. When we say that it's a 120 volts, what we really mean is that the effective value for that outlet is 120 volts. That when you plug something in, it's equivalent to plugging into 120 volts of DC. The maximum value, that sinusoidal varying voltage that is actually the output of your outlet, is actually that 120 times the square root of 2, which I think is about 160 volts. And it's oscillating between positive 160 and negative 160 over one cycle. But that effective value is going to tell us essentially what is that equivalent to in terms of DC. We're going to talk a little bit more about this later.